Okay, good evening everybody. So here we are going to give you some hints regarding solution of assignment 2, and before proceeding to solve the problems, I would like to first tell you something about the Dirac delta function which we have come across. So what have we seen in the class that if we define our electric field, let us, this is, we are talking about Dirac delta function. So what have we seen in the class, that in the lecture sir has told us that if our electric field varies as 1 by r square r cap. So if we take the divergence of electric field, let us say if we calculate divergence of E in a spherical polar coordinate system, we get it as 1 by r square del by del r of r square into 1 by r square, which comes out to be 0. But meanwhile, we also know that divergence of E d tau should be equal to E dot dA from our divergence theorem. We know this. So if you calculate E dot dA in spherical polar coordinate system, let us say we calculate E dot dA, and we know that our E varies as 1 by r square and our dA will be radially outwards. This will be r square sin theta d theta d phi. So E dot dA will become something like this. This will be, and we are calculating at, let us say, radius r. The radius of the sphere is r. So it will come out to be 1 by r square into r square sin theta d theta d phi, where the integration runs over. I have taken already the value r, so this will be theta will go from 0 to pi and phi will go from 0 to 2 pi, and we will get, it will come across 4 pi. So if we see equation 1, let us say equation 1 and equation 2, there is a contradiction. According to divergence theorem, this should match with, they should be equal, but we see that divergence of E is 0, hence the first left hand side is 0 while the right hand side is some finite value, it is equal to 4 pi. So there is some problem. So what is the problem? We are trying to find a solution. What is the problem lying here? The problem is that when we are writing our E, let us say proportional to 1 by r square r cap, we are neglecting the value at r equal to 0. What is happening at r equal to 0? We can see that the electric field blows up at r equal to 0. So to define such ambiguity, we will define a function that is called delta function, such that our delta of x is 0 for x not equal to 0 and infinite for x equal to 0. This infinite is in some other sense, it means that, let us say in our case, if we put charge, let us say I put charge equal to or let us say r equal to 0. So if I use this formula to find the divergence, I will never find my divergence, because my q itself is situated at origin and it will blows up. So just to cover that ambiguity, we are defining this function that is called the delta function. So there is a property of delta function that minus infinity to plus infinity delta x dx, we have normalized it by 1 by 4 pi. So this is the delta function. In fact, delta function is not a function, it is called a distribution. We call its delta x is also called distribution function, let us say distribution function. Means it takes values at that point where x equal to 0, otherwise it is 0. So let us say we will solve some question, we will say some limiting case. Let us say I define a rectangle of unit area. Let us say I define rectangle of unit area such that its sides are of side n and it is height is, and height is 1 by n. So if I push my n tending to 0, if I, my area is always 1. So if I take the limit that my area will be always n, and I put limit n tends to 0, then what will I get? Let us say I will get something, if I take n correspondingly equal to 0, this will be my shape at x equal to 0 origin. So it's kind of means my rectangle function, or my rectangle also goes to a delta function if I take the area always equal to 1 and I push on, I keep on decreasing the width. So this will become a delta function. Also a triangle, let us say it's a triangle of area 1, and I keep on decreasing the base. So at some time, let us say it is n, and I keep on, my n tends to 0 and the area remains constant. Let us say area remains constant and my n tends to 0. So it will keep on increasing like this. Well, it is little bit wide, but it will keep on increasing like this. I will get a spike function. This we can say that is a limiting case. At n tends to 0, they will, means these functions will go to delta function. So these are the examples. Also the Gaussian function, if you remember the Gaussian function, they also, if we keep on reducing the width, they will go to delta function. So these are the examples of delta function. So let us say there is a problem in Griffiths 1.44. Before solving problem, let me introduce some properties of delta function. So here are they. Delta of minus x is delta of x, delta of x. X delta of x is 0. Delta of, let us say a is any constant, x is 1 by mod a delta of x. Delta of x square minus a square is 1 by 2a delta of x minus a plus delta of x plus a. These are the properties which we will use in solving problems related to delta function. Let us solve a question. There is problem number 1.44, which says that evaluate 0 to 2 x cube plus 3x plus 2 delta of 1 minus x dx. So how will you solve this question? A very simple way, use property 1. So this is equal to 0 to 2 x cube plus 3x plus 2 delta of x minus 1 dx, and we can see that x equals to 1 lies in the interval between 0 to 2. So this will be equal to 1 cube plus 3 into 1 plus 2. So this will be equal to 6. Now there is a very simple question. Let us say what will happen if I evaluate let us say anything, x cube delta of x minus 3, and it goes from minus 2 to 0 dx. So if you will be little bit negligent, you can write it as this is equals to 3 cube, but it is wrong. The reason being that x equals to 3 does not lie between, does not lie between the interval specified, that is from minus 2 to 0. So for that's why it is 0. So the correct answer is 0. So while making substitution of the value of the delta function, also to be really careful with the derivative also. Sorry, not derivative, with the interval of the function, that the value where delta function corresponds should lie between that interval, otherwise it will be 0. Question number, let us say 1.45, which the question is, show that x d by dx of delta x is minus delta x. So we are supposed to find this integral. How will you do it? Simple. Just evaluate minus infinity to plus infinity fx x d by dx of delta x dx. Just evaluate this. I hope that you know how to do the integration by parts. Take it as u and take it as v and do it. You will become, the solution will be like this. This will come out to be x fx delta x from minus infinity to plus infinity minus infinity to plus infinity d by dx of x fx delta, this will be like this, ffx delta x dx. But this will give me 0 because delta of minus infinity is 0 and this is also equal to delta of infinity. So I will left with only minus infinity to plus infinity, and upon differentiating you can write x f prime x plus fx multiplied by delta x. And as from our previous slide, from property let us say where it is, from property 2, you know x dx equal to 0. So whatever be the function is, where it is, so this will give me 0 and I will left with minus of plus infinity to minus infinity to plus infinity fx delta x, and which proves our result from 1. Let us say we got it, that we have got the same function with a negative sign. Yes, exactly same. So this will be hence proof ना, तो हो गया ठीक. हाँ, now problem 1 point, let's say problem, I am doing the problem 2.20, which shows that which one of these is an impossible electric field. So from today's lecture, let's say from 13th lecture, matlab on lecture on 13th January, we have seen that for any electric field to be true, what should happen, that the curl of that electric field should vanish, that we know. So the electric field is given as first one, let's say E, a vector is, let's say some k times xy x cap plus 2yz y cap plus 3xz z cap. Find curl of E find it. This is, I am leaving it to you, and if my curl of E is 0, then it is a possible electric field, and if curl of E is not equal to 0, that is impossible. So I am leaving it to you. The second electric field is given as let's say some constant equals to k, some constant y square x cap plus 2xy plus z square y cap plus 2yz z cap. Do the same thing and you will find that here the curl will vanish. You will get that the curl will be vanish here. So this is a possible electric field, but this will not. The rest is only mathematical step, and I hope you will do it. So problem number 2.21 or 2. But this problem says, but excuse me, थोड़ा सा कट कर लीजिएगा. Okay, thank you. So now problem number 2.21. So what we are supposed to do here, we are supposed to find the potential due to a solid sphere. we are supposed to find a solid sphere at some point, let's say r, where r is maybe less than r. Matlab we are supposed to find the potential inside the sphere of radius r. So, suppose this is a sphere, uniform sphere of radius r, and we are supposed to find, let's say at some point, I am saying this, let's say r, this is my r, we are supposed to find the potential at that point. So, how will we solve this? There are two ways of solving this. So, I am doing the first way, which is the straightforward way, first way. What we will do, we will use the electric field to find the potential. So, we know that electric field, I must hope that you have done this by now, that electric field due to a solid charge sphere for a sphere, that is charge sphere, solid sphere, is given as 1 by 4 pi epsilon naught q by r square r cap for r greater than r, and this is 1 by 4 pi epsilon naught q by r cube So, this is the field due to a uniformly charged sphere. So, if we know the electric field, we can calculate V very easily. Let's say this is my sphere of radius r, and I want to calculate the potential at this point, let's say on r. So, my reference point will be anytime anyway infinity. So, how will I introduce? Let's say for r greater than r and up to the surface, how will I calculate? My V of r will be minus of infinity to r 1 by 4 pi epsilon naught q by r square dr. This is my electric field E dot dr, and my dr is also radially outwards, my field is always radially outwards. So, dot product will give me just this. And this is a very straightforward formula, you can calculate. This will be q by 4 pi epsilon naught r, and let us say for r less than r, that is a point inside the sphere, do the same thing. We have already know what is the electric field inside the point, but just do the calculation and the result will be something like this. V r less than r will be q by 4 pi epsilon naught 1 by 2 r 3 minus r square by r square. I am leaving the second part calculation up to you. This is simply just an integration over r, nothing else. Now, the most important thing is the second way of thinking, that how can we find out the another way of solving this. Another way is like this. Let us say I am having a sphere and I want to calculate the potential at some point r. So, let us say here. So, what I will do, I will assume that this is my sphere, and just I will, for this calculating r at this point is equivalent to calculating Vr due to inner sphere plus calculating Vr due to the spherical shell which runs from r to r. So, what I am saying that let us say for the inner sphere, my V in is given by 1 by 4 pi epsilon naught q enclosed by r. So, what we are supposed to do, we have to find out what is the q enclosed for the inner sphere, and if the density is charge density per unit volume is rho, I can write it as 1 by 4 pi epsilon naught q enclosed will be nothing but 4 by 3 pi r cube by r, and I will get V in is rho r square by 3 epsilon naught. So, this is the potential due to inner sphere. Now for the outer spherical shell, what is the potential? That is also very obvious. What I have to do is V will be my, I am leaving the calculation up to you, same formula, same thing, only V is rho by epsilon naught R by R. The outermost spherical shell will go from R to R, and this will be R prime dr prime. Just integrate it, everything is quite simple, and total V will be add V in plus V out. Total V will be add V in plus V out. We will get the same expression, that is Q by 4 pi epsilon naught 1 by 2 R cube 3 R square minus R square. Same answer. So it's a way of thinking. Means just let's say I have to what I have done means calculating potential at this point. Sorry, at this point is equivalent to calculate the potential due to inner sphere and plus calculate the potential due to the spherical shell at that point. And just after everything, I will add it up, and it's as simple as this. Now, next question is problem 2.39. Problem 2.39. So problem 2.39 is related to electric field inside conducting sphere, means metallic sphere. You can say something which conducts electricity. Or so what happens in a conductor? The electric field inside is 0, means the conductor is always incorporates its charge in such a way that even if you put a q charge inside something, it will make the electric field inside 0. So it's based on the same principle. How? It says that two spherical cavities of radii A and B are hollowed out from interior of metallic conducting sphere, and at the center of each cavity charge QA and QB is placed. So what it says something like this. So this is my sphere and this is conducting sphere of radius r. We are hollowing out two cavities. Let us say there is a cavity of radius RA, this is a cavity of radius RB, and I am putting a charge, let us say QA here and charge QB here. Now, the first part of the problem is find surface charge sigma A and sigma B and sigma R. So what I want to tell you here is that this is a conducting sphere. So this QA, for in a conductor we know that this QA will attract negatively charged electrons around the cavity such that they will just try to oppose it. For QA, this negatively charged hole will be minus of QA. Similarly here, this plus QB will again attract negatively charged electrons from the conductor such that this sum will be, the surface charge here will be exactly equal to QB, and in the same manner, sorry, minus QB. Now for these charges minus Q and minus QB, this surface will accommodate positive charge such that the field inside is 0. So if you calculate the whole, this will be adding these all will give me positive charge, will give me QA plus QB. Now we can, after drawing this picture, we can easily answer question number A. The first question says that find surface, we have to find sigma A, sigma B and sigma R. It's very simple. For sigma A will be, what is this? Sigma A will be, क्या हो गया, कुछ क्लिक हो गया क्या? भैया थोड़ा स्टॉप कर दिए कुछ. Thank you. So sigma A, that is the surface charge for this QA, will be, we know that for this sphere, the little bit is small size cavity, the charges are minus QA by 4 pi A square. Similarly, my sigma B will be minus of QB by 4 pi A square. But for the whole sphere, the charge on the surface is QA plus QB. So my sigma R will be nothing else but QA plus QB divided by 4 pi R square. It's that simple. Now the second part of the question says field outside the conductor. So what is the field outside the conductor? Very simple. We know whatever be the cavity V, we know that the charges here on the surface are QA plus QB, and we know that field is 1 by 4 pi epsilon naught Q total by R square. So in this case Q total is QA plus QB by R square R cap. Let's say for some for R greater than R, this will be R square. The third part of question says what is the field within the cavity? Field within the, again this is the sphere, this is my cavity, let us say the charge is here. If I am interested in finding the field here, let us say RA, not RA exactly, we have put some RA, let us say R. So for that spherical surface, we know that field will be nothing but 1 by 4 pi epsilon naught QA by RA square in pointing along the radial direction, and same goes for Q, the second cavity, that this is RB, this is QB, and I am supposed to calculate the field here. So for this field I will be having my electric field vector, this will be in vector sign, will be 1 by 4 pi epsilon naught QB by I will not say it exactly RA, let us say at any R, because RA we have defined the radius of R. So let us say R square, but in RA direction, but in this case this R is less than RA, it should write it, the condition is here. Similarly here I will not write RB, this is Q by R square RB cap, but the condition is R should be less than RB. So these are the electric field inside the cavities. And force on QA and QB. So we know that this is a conductor, so it will already incorporated negative charge here. So the force and QA and QB will be 0. It seems that QA will never see QB, and similarly QB will never see QA. So we left with problem 1.20 actually. So what problem 1.20 says that is there any vector, or calculate a vector that is divergenceless or even curlsless. So we are supposed to find any vector. Let us say U is any vector, you have to find which has 0 divergence and 0 curl. So the condition is divergence of U should be 0 and curl of U should be 0. So it's very easy question. Just write the let's say U is any let's say U is any Ux I cap plus Uy j cap plus Uz k cap, and divergence of U 0 means my del of Ux by del x plus del of Ui, sorry this is U actually, sorry, del of Ui by dy plus del of Uz by dz is 0. First condition is this, and when I am saying that curl of U is 0, I mean I will take the curl like this, del by del x, del by del y, and del by del z, Ux, Ui and Uz equal to 0. this will also 0 vanish. So we will vanish one by one element. Let's say the vector corresponding to I cap goes to 0, the component corresponding to j cap goes to 0, and the vector corresponding to k cap goes to 0. So if we are looking at I cap, let's say this means del uz by del y minus del uy by del z equal to 0. And we will get three conditions like this: 1, 2 and 3. So upon solving this, we can find the answer of u. One of the example is, let's say if I take ux equal to y plus z, uy equals to z plus x, and uz equals to x plus y. These are my choices. So if I put this, I will see that my divergence of u and even curl of u is 0. So this may be a possible answer, but you can find it from here also. So this is a very simple problem. So the rest of the question, that is problem number 1.57 and problem number 2.26 and problem 2.47 will be done by Ravit. The rest problem, that is problem number 2.21, 2.26, 2.34, 2.35 are left for the students to solve. These are very easy questions, and that's all for this assignment.
Okay, hello, my name is Rabit Singh. I'll give some hints from some problems from the assignment number 2, because some hints has already been given by Anmol. So I'll first problem is 1.57. We have to find out the line integral v dot dl for a given vector v along a path shown in the figure, that is from O to 1 0 0, 1 0 0 to 0 1 0, then 0 1 0 to 0 1 2, and come back to the origin. The information needed to solve this problem is, while doing the line integral, keep in mind the r and theta dependence along this path 0 1 0 to 0 1 2, and along the path 1 0 0, that is this one to this one, see that theta is pi by 2, and our line element is r sin theta d phi phi cap, that is this is our line element. This is r sin theta d phi phi cap. So to verify the Stokes theorem and to check the answer of your line integral, do the surface integral by breaking the surface into two parts. That is, first one is SA in the xy plane, second one is SB into the yz plane. So just remember that the just keep in mind that in the xy plane your surface element is r sin theta, because in this plane this is just r sin theta, then you increase it y dr, and your surface element is just this one. This is your r sin theta d phi. So your surface element is r sin theta d theta dr phi cap, theta cap, sorry, because this is just in this direction, which is negative of the theta cap. And in the yz plane your surface element is r dr d theta dr, which is in the negative of phi cap direction, because your phi is varying like this, phi cap is perpendicular to this surface. Our next problem, which is 2.27, you are given a conical shape at which you are provided that the surface density on this conical shape is sigma. You have to find out the potential difference between potential difference at point B, this is B, and A, this is your A. So, what are you given is the height of this conical shape is h, and the radius of this circular top is capital R. So, the information needed to solve this problem is the following. What you do, you just divide the conical shape into the rings of infinitesimal width dl. So, this is your dl and radius r, this is your radius r, this one is radius r as shown in the figure. Note the relation tan theta, which is, suppose this is theta, your theta, then you can see tan theta is equal to r over z, whether you write r over z or capital R over h. So, these quantities are depending on each other, that is z depends on L, and so using this information, what you do, you just add up the potential due to these rings, to find out the potential at point B and at point A, then find out the potential difference between A and B. So, that is all. And in problem number 2.47, you have to find out the, you are given a uniformly charged sphere of radius r. So, this is your charged sphere of radius r. Total charge on this sphere is capital Q, let me capital Q. So, the charge density, which is uniform, rho will be given by Q over 4 by 3 pi r cube. So, if we take a sphere, a small sphere, inside this sphere of radius small r, the charge enclosed by this sphere will be Q equal to 4 by 3 pi r cube into charge density, which is Q r cube over r cube. So, you have to calculate the force applied. So, what is your problem? Let us call half of this sphere is southern hemisphere and left part is northern hemisphere. So, you have to calculate the force applied by the southern hemisphere to northern hemisphere. So, to find out the force, just consider a charge element d tau in the northern hemisphere. So, the charge element will be rho d tau. So, if we calculate the force on this charge element, that is d tau, rho d tau, that force I have represented by df cap. So, df cap will be along the r cap direction. Now, see by this spherical symmetry, the horizontal component of this force, which we call df sin theta, will be cancelled out as you move in the phi direction, and the vertical components will be added. So, to find out the force due to the southern hemisphere to northern hemisphere, you have to add these forces. So, adding means just you integrate on this force, that is df cos theta. So, keep in mind your theta integration will be from 0 to pi by 2, because you are calculating the force on the hemisphere. So, your theta will vary from 0 to pi by 2, which is because you can go from only here to here, sorry, here to here. Then so, after that, so as you know already that electric field at point at this point, which is called P, at which we are calculating the force, will be equal to k q over r square, where q is the charge enclosed by the sphere of radius r. So, your total force will be just electric field into volume element which is rho r square sin theta dr d theta d phi, then you are adding only vertical component, that is df cos theta. You just do it this integral to find out the answer. Thank you. I hope with this information you guys can solve these problems. If you still have any doubt, please share with us on the Google forum. Thank you.